This is problem 81 from chapter 14. When S is equal to 0, the spring on the firing mechanism is unstretched. If the arm is pulled back such that S is equal to 100 millimeters and released, determine the maximum angle theta the ball will travel without leaving the circular track. Assume all surfaces of contact to be smooth, meaning no friction. Neglect the mass of the spring and the size of the ball. Although we're neglecting the size of the ball, we cannot neglect the mass of the ball, but they didn't give it to us. However, problem 80 is very similar, and in problem 80, the mass of the ball is 0.3 kilograms, so we're going to assume that the ball in problem 81 has the same mass, and this will give us the answer that is in the back of the book. So, I'm going to use my work-energy relationship, which says 1/2 mv1 squared plus mgh1 plus 1/2 ks1 squared plus the work done by forces other than the spring force and gravity is equal to 1/2 mv2 squared plus mgh2 plus 1/2 ks2 squared. And usually a lot of things in this equation will be equal to 0, and that's true in this problem also. So let's see, you are pulling it back, pulling the arm back and releasing it. The ball is starting from rest. I don't know that they actually said that in the problem, but it would be starting from rest. And let's say the datum is here. And so the initial gravitational potential energy is 0. Let's look at the ball when it's at some point on the track. Here you have a force of gravity acting downward. You have a normal force perpendicular to the surface of contact. Does the normal force do any work? No, because it is perpendicular to the displacement in this case, as in many other cases that we have seen. That does not always have to be true, remember, but the object is moving on the surface, so the displacement is perpendicular to the normal force, and that is the only other force we have because there is no friction. So that is equal to 0, so we just have the elastic potential energy on the left-hand side of the equation. On the right-hand side of the equation, we're looking for the maximum angle the ball will travel without leaving the smooth circular track. Now, remember in the previous problem we looked at with the roller coaster cart, you have to have a minimum velocity to be able to go upside down without falling off. So we're going to have something similar here. When the normal force goes to 0, the velocity is not 0. So we still have some kinetic energy. We still have gravitational potential energy. The spring's no longer touching the ball, so we don't have any elastic potential energy. So now we have 1/2 ks1 squared is equal to 1/2 mv2 squared plus mgh2. And you can see from this equation that we do need to know the mass because it doesn't cancel out, because it doesn't appear in the elastic potential energy. Do we know K? Do we know K? Yes, we do. It wasn't given in the problem statement, but it is here. So K is equal to 1500 newtons per meter. S1 is equal to, well, 100 millimeters. That would be 0.1 meters. And they have defined S here so that it is the same as the S that we have in the equation here. So this is 1/2 times 1500. So this is the stretched, S is the stretched length minus the unstretched length, which is the difference that they're giving us here. So this is 0.1 squared is equal to half the mass, which is 0.3, times v2 squared plus 0.3 times 9.81 times the height. Well, now we have a problem because I have two unknowns and only one equation. I could simplify this a little bit. I don't really think it's going to be worthwhile to do it at this point. So instead, let's think about where we can get another equation from. So we're going to call this equation 1 and save it for later. Well, there's another piece of information that I haven't used. So I know that I'm looking for the maximum angle. So if, well, the ball's just about to lose contact, so the normal force is equal to 0. This is similar, again, to what we did in the previous problem, only we may not be at the very top of the loop. Now, do you think that the ball is going to fall off the track before the angle theta here becomes 90 degrees? Well, now, that is something to consider. Actually, it's not going to fall off of the track, but if it's not going fast enough, it might never make it up until 90 degrees, to 90 degrees. So it's not going to fall off. It just might be that it never gets to 90 degrees. However, let's assume it does make it past 90 degrees, and so it would be just about to fall off the track at theta max. So let's say we're going to assume the angle is greater than 90 degrees, and this is when at our maximum angle, the normal force is equal to 0. Okay, now remember in problem 73, we used Newton's second law in the normal direction, and we're going to do the same thing here. So I want to draw a free body diagram for the ball when it is at an angle which is greater than 90 degrees. I have the force of gravity acting straight downwards, and that's it, because at the maximum angle, the normal force is equal to 0, and I have no frictional force. Now, I must have a force pointing in towards the center of the circle if the velocity is not 0, because we have mv squared over rho. This is the acceleration pointing in the normal direction. If something's going in a circle, it has to have acceleration pointing in towards the center of the circle unless the velocity is 0. So if we didn't make it to 90 degrees, so if the ball just went up like this and then it stopped and then it turned around and went back that way, then you'd have a velocity of 0, and so you wouldn't have a net force in the normal direction, but you would have a normal force. So in that case, the normal force pointing in towards the center of the circle would be balanced by the component of the force of gravity that you have pointing this way. So if you don't make it to 90 degrees, the normal force would not be equal to 0 at the maximum value for the angle theta. So let's go back to what we have here, and this angle theta is not the angle that I want to use, so I'm going to use a different angle which is 90 degrees less than theta max, and I'll just call that angle phi. This makes things easier because I can break now the force of gravity down into components, and if this angle is phi, this angle is also phi, and so this would be mg cosine phi. I think that's actually the only component I need, but you'd have mg sine phi there. Okay, so looking in the normal direction, oh, wait, I'm looking up here, so pointing in towards the center of the circle, that would be the sine component, so the sine component is the one that I need. Okay, so I have mg sine phi is equal to mv squared over rho. So the mass cancels out. I want the velocity because I need that for equation 1. So this is the velocity 2 that we have here. So that's equal to the square root of g times rho times sine of the angle phi, and just compare this to what we have here. So this is just the square root of g times rho. This is the square root of g times rho times sine of the angle. Okay, so we can take this and put it in our equation here. However, I got rid of my unknown velocity, but I introduced a new unknown, which is this angle. But fortunately, I can relate the height to this angle. So if I'm at 90 degrees, then I'm at a height of 1.5 meters. So the distance from here to here is 1.5 meters. 1.5 meters is the radius. So this is 1.5 meters, and I need, in addition to this 1.5, I need this distance here, and that would be 1.5 times sine of the angle. So height 2 is equal to 1.5 plus 1.5 times sine of phi, but we could write that as 1.5 times 1 plus sine of phi. So now, for equation 1, I have 1/2 of 1500 times 0.1 squared, which is 7.5. That's equal to 0.3 divided by 2 times v2 squared. v2 squared would be g times rho times sine of the angle. The radius of curvature is just the radius, because if the object is going in a circle, the radius of curvature is the radius. So this is 9.81 times 1.5 times sine of the angle plus 0.3 times 9.81 times height 2 is 1.5 times 1 plus sine of the angle. We can do a little bit of rearranging. Well, first, 0.3 divided by 2 times 9.81 times 1.5 is supposed to be equal to 2.207. Let me just check to make sure this works out. Okay, so that looks good. So it's 2.207 times sine phi, and then 0.3 times 9.81 times 1.5 is 4.415. And that's 1 plus sine of phi. Then the 4.415 times 1, I'm going to bring over to the other side, so that's 7.5 minus 4.415, which is equal to sine of phi times 2.207 plus 4.415, and then finally we get the angle phi is equal to the inverse sine of 7.5 minus 4.415 divided by 2.207 plus 4.415, and that gives me 27.8 degrees. And then finally, theta max, because of the way I define the angle here, would be 27.8 degrees plus 90 degrees. So that is, let's round it and call it 118 degrees. And that concludes problem 81.